Welcome. We are doing 98, 99, and 100. Let's do it. Now, 98 is a tricky one. Probabilities, we don't talk a lot about probabilities, but we talk about probabilities in statistics. This is an age-old truth that if events are mutually exclusive, they cannot be independent. I'm going to make like a little picture. Mutually exclusive. So okay, so I made a little picture with a Venn diagram. Mutually exclusive would be two events. And normally the common phrase is not mutually exclusive. We're like, wow, she had blue eyes and brown hair. And it's like, wow, blue eyes, brown hair, they must not be mutually exclusive, meaning there should be some amount of overlap. So again, if you drew a picture, if one circle was brown hair and one circle was blue eyes, like me, I would fit in the middle, and they're not mutually exclusive, okay? But what this says is if they are mutually exclusive, then there's going to be some type of an independent. There's going to be some type of dependence. So knowing that I have brown hair helps to figure out what color eyes I have. That's pretty interesting, doesn't it? So when somebody tells me they have brown eyes and I've never met them, I can probably assume that they have darker color hair. If someone tells me they have blue eyes, then I'm thinking their hair might be quite a bit lighter. That's dependence. So once again, if they're mutually exclusive, meaning they can't happen at the same time, that's what that means. I'm going to write that in my notes. Can't happen at same time. So if they're mutually exclusive, they can't happen at the same time, then that would mean that there must be some type of dependence when calculating that outcome. Therefore, E is correct. It says if they're mutually exclusive, then they cannot be independent. They must therefore be dependent. Some people just memorize that, okay? If they're mutually exclusive, they can't be independent. Now, there is an exception to that. If the probability of one of the events is 0, but remember they started the question off saying it can't be 0. So let's go to the next one. 99, a consultant of statistics reported the results of an experiment. Okay, they came right out and told us experiment. They did the calculations and came to a p-value of 0.24. So right away, am I walking through door 1 or door 2? I'm thinking door 2 because my p-value is greater than alpha 0.05. Therefore, if I walk through door number 2, it says fail to reject the null hypothesis. When you fail to reject the null hypothesis, you do not have sufficient evidence to show H sub A. So I'm looking for, I do not have statistical evidence, so I'm immediately ruling out A and B. Now I keep reading. It says the other ones go off track. 2 times as many? No. 96% of the observation? No. C and E seem to go off track. So D matches my definition of what a p-value actually is. If I did this experiment many, many times, and I end up getting a p-value of 0.02, that is not evidence because that would in fact happen if the null hypothesis is true. We'd expect to get that test statistic at least as extreme as observed 24% of the time. 0.24 was our p-value. Next question. Looking at this one, I jotted this on my paper. So while I read the question, think about this. If you actually did this question as a free response. It says a new medication developed to treat insomnia. Researchers compared the 2 drugs. One used was in the past, and we compared the length of time it takes to fall asleep. What method should you use? So if you were actually doing this, you want to find the average or the mean amount of time it took to fall asleep for the old medication and compare it to the mean of the new. And your H sub A is you believe that they're not the same. And so by doing this study, you're trying to prove, you might figure out the old one's better or the new one's better, or they're pretty much the same. This is how we'd set up the null and the alternate hypothesis. So now let's take a look a little bit deeper into the question. The only one that's actually comparing them, have this subject choose, no. When we make a choice, we might believe, well, I know my choice was better. That won't help us compare. Assign the two drugs based on their past sleep history without, everyone knows we don't design experiments without randomization. Come on. 3, give the new drug to all the subjects the first night. Again, now we got confounding variables. Maybe people just get better sleep the first night or worse sleep the first night. That's entering a confounding variable there. Randomly assign 2 subjects, giving the new drug to one group and no drug. Okay, no drug, huh? That's really, if you selected this one, notice if I don't use any drug at all, it only will prove to decide if that new drug works. It won't help me decide if it's better than the old one. So there's nothing wrong with D, except that's not, we're trying to figure out what the best method is. So that means our answer is E. Thank you for joining us.